Hello, and welcome back to Aggressive Physics. Today is day 10, where we're going to discuss free fall and the difference between mass and weight. Now, free fall is when an object is caught near the Earth's gravitational pull. Any object dropped near the surface of the Earth will be pulled downward by the Earth's gravitational pull at a rate of 9.8 meters per second squared. That's our standard value for the acceleration of gravity near the Earth's surface. We have to go pretty far in order to have that value decrease significantly. In order to have a more casual value, we can round that to 10 meters per second squared, or we can be a little more formal and use 9.81 meters per second squared. The value in the reference table is listed as 9.81 meters per second squared. So the reference table likes to be a little more formal. But when we're calculating casually for maybe a classwork or a homework, 9.8 or 10 is an acceptable value. Now, acceleration is a vector, so direction matters. And although we don't say it often in our everyday language, the acceleration of gravity is always acting downward. Now, mathematically, we're talking about objects that are moving vertically when we drop them in the Earth's gravitational field. So we have, if you're looking at a graph, the y-axis. When objects move up in the vertical direction, we use a positive value. And when objects move down, we call that a negative value. So the acceleration of gravity should be written when we use it in problem solving as negative 9.8 meters per second squared, negative 9.81 meters per second squared, or negative 10 meters per second squared. In the English system, it's 32 feet per second squared. So if you're using feet as your value, as your distance value, you'd use 32 as the value. But since we're going to use the metric system in this course, 9.8 is our number. Make sure you always include the negative sign, or else the numbers will not work out mathematically. The equations we use utilize the fact that the vectors will be included. They're vector equations. So using a negative sign for denoting backwards or opposite of the direction of motion will allow us to calculate the proper answer when we solve problems. Typically, when we denote direction, to the right is going to be positive, to the left would be negative, up would be positive, and down would be negative. On an xy coordinate system, positive x, positive y, and negative y are the same as you would use in a math class. So that's why we stick to the same convention. But remember, acceleration is a vector, so direction does matter. Now, the question most people have is whether or not mass will affect the acceleration. This is a question that dates back from the early physicists. Galileo, in fact, purportedly went to the top of the Leaning Tower of Pisa to determine whether or not this was true. And he took different size cannonballs, is the story, some grape shot, and then cannonballs, and maybe some musket balls or something like that, and dropped different sized spheres from the top of the tower. Now we can simulate that as well here in the classroom, here in your house, or wherever you're viewing this this video. And all I'd like you to do is take a pen and a marker or something a little heavier than the pen and drop them. If we drop them from a certain height above a table or the floor, you'll notice that they land at approximately the same time. The difficult part is dropping them simultaneously. If we do the same thing with a marble and, let's say, a lacrosse ball, something that has the same shape but different mass, you'll notice the same thing. Although the marble is significantly less massive than the lacrosse ball, it will still land at the same time. In addition, if we were dropping a softball and a piece of paper, that's a significant difference in mass as well. Unfortunately, though, the paper will take longer to hit the ground. A classic physics experiment is using a penny and a feather to denote whether or not mass affects the acceleration. Now, although the acceleration of gravity is the same for each, why would the piece of paper or feather drop differently than the marker versus the pen, or the marble versus the lacrosse ball? And the reason that is the case is because there are other forces acting on the piece of paper that are not acting on the other objects. In fact, every object dropped near the Earth's surface is going to experience wind resistance or air resistance. But when we're dropping a sphere and another sphere, the air resistance is minimalized. When we have the surface area of the paper, or a feather, which has large surface area compared to the spheres that we're dropping, they're going to experience a greater amount of air resistance or wind resistance or friction. In physics, especially in introductory physics course, we typically ignore the effects of wind resistance as long as we have an object that has good aerodynamics. So the bottom line is the wind resistance will actually affect the rate of acceleration. Later, when we talk about forces, we'll be able to show the difference between the force of gravity acting down and the force of wind resistance or air resistance, or we often call it drag, acting up when we're dropping an object. For the time being, we're going to ignore the effects of air resistance. We're going to use objects that can cut through the air quite efficiently. A sphere will have minimal air resistance or wind resistance, or drag if you call it that, and they'll fall at a consistent rate. The acceleration, if we were to calculate it in the lab, might be 9.78, might be 9.75. If we were to drop a piece of paper or a feather, we may find that the acceleration is much less, maybe 1 meter per second squared, if it falls at a constant rate at all. In fact, what most objects will do if there is wind resistance will experience a situation where they will fall to a certain point, accelerating, and then fall the rest of the way at what we call terminal velocity. The wind resistance and the force of gravity will be equal, and you'll find that there's no more acceleration. Now, that's a state of equilibrium because the force up and the force down are equal. However, it doesn't mean that the object will stop moving. It will just stop accelerating. So you need to have an extra force on an object in order for it to accelerate. Now, when we drop an object near the Earth's surface that has good aerodynamics, you'll find that it will fall with a net force, and that net force will typically be the force of gravity. Now, the question is, what is the difference between mass and weight? Well, mass is the amount of stuff that makes up the object. The weight, on the other hand, is the pull of the Earth on the object. So what happens is, in order to find the force of gravity, we multiply the mass of the object times the acceleration of gravity. That will get us the force of gravity. The mass is constant no matter what. The force of gravity may change due to aerodynamics. But like I said, for this course, we're going to stick to most objects that do not have maximum drag or wind resistance. We're going to stick to objects that cut through the air aerodynamically and have minimal drag on them. Now, scientists have actually taken this when we went to the moon and verified it. The moon has no atmosphere. It has no wind resistance. There's no drag. So they took a feather and they took a hammer and they dropped the two simultaneously on the moon's surface. Well, since there's no atmosphere, they both fell at the same rate. And you can find a video of that on YouTube. If you type in feather hammer experiment or feather hammer on the moon experiment, you'll be able to see an example of that. Now, what's important to realize is that the acceleration of gravity on the moon is less than the acceleration of gravity on the Earth. So they will fall at a slower rate, 1.63 meters per second squared. However, they'll both fall simultaneously. So the feather and the hammer will actually fall together. We could simulate this in the lab or in the classroom with a demonstration where we have an evacuated cylinder where we suck out all the air, we create a simulated vacuum, and we put a penny in a feather or a penny in a piece of paper in that cylinder, and we allow them to fall at the same rate. And you'll see that evacuating the air from a small container will simulate the vacuum of the moon in this case, or the vacuum of space, and the objects will fall at the same rate. Now, what's interesting to note is that when we talk about space, we often talk about zero gravity. And one of the things to note is that there is no such thing as zero gravity. There's no place where we can go where there's no gravitational pull on an object. In fact, when astronauts are in a space shuttle or the space station or orbit the Earth, they are constantly in free fall they're actually falling towards the Earth at 9.8 meters per second squared. But because they're moving forward at such a high rate of speed, they're able to fall at the same rate that the Earth is curving out from underneath them. So they stay the same height away from the surface of the Earth. So they fall but never get closer to the Earth's surface. Any object that's in orbit around the Earth is actually experiencing this same apparent weightlessness. So what happens when astronauts go into space is they are constantly falling towards the Earth but never getting any closer. It's an endless battle where they try to get to the Earth's surface because the Earth is pulling them closer. Now, at that distance, the acceleration is less than 9.8, but they are never reaching their goal of getting to the Earth's surface. Now, eventually, with space stations or satellites or any object that orbits the Earth, what will happen is they'll slow down. And as they slow down, they'll eventually win that battle because you have to go a certain speed to orbit. So as you decrease the speed, objects will start to spiral in towards the Earth. Once they hit the atmosphere, typically satellites will burn up. Even old things like the Space Lab that was launched in the 70s eventually lost energy and fell to the Earth's surface. But there is no such thing as zero gravity. Often we should call it microgravity, where it feels like you are floating. And in fact, what's happening is the shuttle or the space station is falling toward the Earth, and the people in the space station are also falling at the same rate. So they experience this feeling of weightlessness, which we call apparent weightlessness, without actually being weightless. They still have weight. They're still being pulled to the Earth's surface. But since they're falling at the same rate as the shuttle that they're in, they experience a floating type sensation. The same thing can be experienced in many rides that people go to in amusement parks. Any ride where you fall towards the Earth at approximately 9.8 meters per second squared, you will feel weightless. Typically, astronauts traveling towards space will have a sensation of sickness. Often the training exercises for astronauts are to go up into a big airplane and then dive toward the Earth to simulate weightlessness. This is called, anecdotally, the vomit comet, because most people become sick when they're riding on this for the first time. So astronauts train near the Earth's surface for this apparent weightlessness in space because of the effects on their body. They have to get used to it. Now, just imagine anytime you drive over a big hill in a car and you feel your stomach rise up, or you feel that queasiness of motion during the downhill part. That is happening constantly for the astronauts, and they experience it over their entire trip in space. Now, what we'll do at this point is some sample problems dealing with free fall. Now, the key is, if an object is dropped near the surface of the Earth, you have to realize that the acceleration is going to be negative 9.8 meters per second squared. That will be what I consider to be a hidden variable. It's something that's not going to be stated, but it's going to be expected that you know that to be true. Objects traveling sideways do not experience the gravitational pull if they're touching the Earth's surface. So an object traveling east or west may not experience free fall. But if an object is falling, it's dropped, it's thrown upward, all of these things will be clues for us to use acceleration of negative 9.8 meters per second squared. The negative is key to make sure that the numbers work out properly in the equations. Now, some problems will be on different planets or possibly the moon. So the acceleration will be based upon where the object is being dropped. If it's not stated, we have to assume that the object is dropped near the Earth's surface, and the acceleration is going to be 9.8 meters per second squared. At this point, like I said, we'll do some practice problems, and that will conclude our discussion of free fall and mass versus weight. Thank you. For this next problem, we're going to take a marble and we're going to drop it from the ceiling of my classroom. Now the distance between the ceiling and the ground is 2.75 meters. Well, I guess that's a little too far away. For this one, we're going to solve for a marble being dropped from the classroom ceiling. So we're going to take a marble and we're going to drop it to the floor. Now the floor is 2.75 meters below the ceiling. So that will allow us to at least have one variable, the distance. Now, since the marble is moving downward and these equations are vector equations, we need to use the proper direction. So the displacement should be negative 2.75 meters. The hidden variable is in the word dropped, and that represents 0 meters per second for the initial velocity. Now the other hidden variable deals with gravity. And we have to remember that the gravitational acceleration on the Earth is negative 9.8 meters per second squared. What we're looking for is how long it will take to hit the ground, which is our time. So, when we plug the numbers into an equation, we need to first find which equation to use. And it looks to me like equation 4 is going to be our equation of choice for this problem. We know the d, negative 2.75 meters. We know that VI is 0 times t plus 1/2 negative 9.8 meters per second squared t squared. This term cancels out because of the 0. So it simplifies to negative 2.75 equals minus 4.9 t squared. And you'll notice in this case I did a subsequent step. I wrote it out, but I do not need to put in the units in this case because I've already done that in the second line. Now mathematically, we divide both sides by negative 4.9. And it will be t squared equals whatever 2.75 divided by 4.9 is. And I have 0.56, and there's other numbers in there too. The units are actually seconds squared. Now, what's important to realize is that this is not our final answer because we need to take the square root of that number. So I'm going to do square root of the answer. So I'm going to do second answer, and I'm going to get t to be 0.75 seconds. Rest assured, this number, 0.56, will be an option if you're doing a multiple choice problem. The people coming up with the exams know what types of pitfalls students can fall in and often give false answers or the incorrect answers based on those mistakes. So in this case, 0.56 would be a choice for those who forgot to take the square root of both sides. Another issue is if you forgot to use the negative 2.75. If we have that as a positive number and we try to take the square root, we're going to have a negative value under the radical sign. And of course our calculator is not going to like that, or it's going to give us an imaginary number. The answer will still end up being the same if we forgot both negative signs. So 2 wrongs would make a right in this case, but try to avoid that pitfall. So a person is going to take a ball and throw it, and at the top it's going to stop. Now at the top of any flight the ball will stop, but a classic question in physics is what happens to the acceleration at that point. Now at this point, although the speed will be 0, the acceleration is still negative 9.8 meters per second squared. It will act on the ball the entire time, even when it stops at the top briefly. So what's important to realize is that the acceleration of gravity is everlasting. It continues to affect the ball the entire trip upward. Now, there's a couple of things that we're given in this problem, and I'll make my givens list. For the problem we're going to solve, we're going to have the ball stop at the top. So I'm just going to start right there. VF is 0. Now, will the ball just hover there when it reaches the highest point? Of course not. But what will happen is it will fall after that, but the scope of our problem is to the top of the flight. So VF is 0. A, negative 9.8 meters per second squared. There was one other variable given, which was VI, 15 meters per second. Since I'm throwing it upward, positive. Of course, the default is positive, but I just want to write that to denote that we know it's positive. And what we're looking for, we're going to find how long will it take and how high will it be. So that means we're going to try to find time and displacement. And what I'm going to do is start with t, just because it's the first one I'm looking for. I'm going to use equation 3. VF equals VI plus AT. VF is 0 equals 15 meters per second plus negative 9.8 meters per second squared times t. Put the negative 9.8 in parentheses. I'll subtract the 15 over, and then I'll divide by 9.8. So 15 divided by 9.8 gets me 1.53 seconds. As far as how high will it be at the top of the flight, I'm going to look at equation 5. VF squared minus VI squared equals 2AD. VF is 0. I'm just going to leave it as a 0 squared. VI, 15 meters per second squared, 2 negative 9.8 meters per second squared times d. Now, this 0 here, I didn't put a unit. And many times that's a judgment call, whether or not the units should be in for the 0. If there's a term that cancels out, we typically allow a little bit of leeway with those units. Either way, when we solve this, keep in mind that this negative sign is outside of the parentheses. So we're going to square the 15 first, and we're going to get 225. That 225 is a negative. Now, 2 times 9.8 is 19.6. That also stays negative because of the negative sign on the 9.8 times d. We're going to divide both sides by 19.6, negative. And we'll end up with d equals 225 divided by 19.6. I already know the answer will become positive. And I'm going to get 11.5 meters. So time is 1.53 and distance 11.5 meters. Since it is a displacement, though, positive 11.5, it will go 11.5 meters upward.